Okay, so this is video number 2 in the series of the buffer videos. So in this one, and the last one, sorry, we looked at what a buffer was, how a buffer was made, and how a buffer actually chemically behaves in terms of removing acidity or alkalinity, which was added to the buffer. In this one, we're going to look now at calculating the pH of a buffer. Okay, so I'm going to talk you through how to do that, and then I'm going to do a few worked examples on that. And you've got lots of questions in your notes which will allow you to, and in your calculations booklet, which you can use also then after that. Right, so the first thing, and this is a little bit dangerous, is that we have the same equation. You can see it on the board here, and it's the same equation that we use for working out the pH of a weak acid. So we need to be very careful, because the assumptions that we make when we're working out the pH of a buffer are different from those that we make when we're working out the pH of a weak acid. So I've said just here in the next line down that the assumptions that we make here are indeed different from those when we're dealing with a weak acid. So if you can remember, when we're dealing with a weak acid, when we were trying to work out the pH of a weak acid, our assumption was that the concentration of the hydrogen ions was equal to the concentration of the anion produced in the ionization of the weak acid. And you can see why that would be. When a weak acid, weak monoprotic acid ionizes, we get one hydrogen ion and we get one A minus. So when we're dealing with a weak acid, that was indeed true. But that worked out fine. For the top line of our equation, we assumed that they were true, and that made life a little bit easier for us from that perspective. Okay, but that is no longer the case when we're dealing with a buffer, and we'll have a look at just I suppose the reasons why that is. So first of all, our A minus this time, so as opposed to our A minus being equal to the H plus, our A minus this time is equal to the concentration of the salt of the weak acid. Okay, so we found out the concentration of that salt of the weak acid unionized, and we said that is our A minus. We'll look at why that is the case in a little minute. And the concentration of HA, in other words the weak acid, is equal to the concentration of the unionized weak acid, and that's the same as per our buffer, as for our weak acid, I should say. Right, but this time, and this is the one that's different, and we need to be cautious here, okay, is that the A minus, so the anion from the ionization of the weak acid, and the H plus ion concentration are no longer equal. So let's have a look at exactly as I've sort of said here at the end. Why is that the case now? Right, well, if we remind ourselves the two equations that go on in a buffer, we'll call them 1 and we'll call them 2 here. And the first one is just a weak acid ionizing to give us A minus and H plus. Okay, now we get a very, very tiny amount of A minus from that ionization, because the weak acid only very partially ionizes. But this time, unlike with the weak acid on its own, we have a secondary source of the anion coming from the salt. And we know that the salt, Na, sodium, whatever that salt happens to be this time, okay, gives us lots and lots, a large amount of the A minus. So unlike with our weak acid just in equation number 1 here, this time we have A minus coming from 2 sources, and that's the reason why our A minus and our H plus are no longer equal. Okay, so you can hopefully maybe see also why, as I said up above, we take the A minus as being the concentration of the unionized salt. Okay, so basically in this instance, this time, we ignore the contribution of A minus from the dissociation of the weak acid. And if this, for example, the sodium Na is 0.2 molar, well, we'll take that as also being 0.2 molar for the sake of our equation. Okay, right. So because our variables are, because our assumptions are different, our rearrangement of our equation to make H plus the subject of our equation, because remember we need to make H plus the subject of it so that we can minus the log of it, which allows us then to calculate the pH of it. So instead of this time having, if I just scroll back up to there, we take an example here of having an acid which is 0.3 molar. We have a salt which is 0.2 molar in concentration. So we can put our 0.3 in here. Remember, that's where our HA goes. Okay. We put our A minus, which we take as the concentration of the unionized salt there. Then we've got to rearrange this to make H plus the subject of our equation, so it becomes, unlike with a weak acid, and this is where you've got to be careful, don't treat it as a weak acid calculation, where it becomes Ka on the HA over the concentration of the A minus this time, gives us our H plus, and then we minus the log over H plus, and there we go, we'll get our answer of pH. So I suppose if you're wanting to memorize a formula for working out the concentration of a buffer from a weak acid and the salt of a weak acid, there you go, that's the one that you need to get there, which is different from that whenever we were doing our weak acid calculations on their own. Right, so let's have a look at a few worked examples. Start off with a really dead easy one here to begin with, but probably a bit daft, it's so easy, but we'll do it anyway just to make sure. So what you might want to do is pause the video, read the question, do the question, and then I know the answer is on the board already, but you can just double check that your answer is concordant with what I got. Okay, so this is dead easy. Calculate the pH of a buffer, 0.5 molar propanoic acid and 1.0 molar sodium propanoate, and there's the Ka given you. So basically it gives you everything here. All you need to do is be able to remember the formula from up above, the one in the big green highlighted circle there, and if you can remember that formula, then all you have to do is plug in the numbers. Okay, so your HA goes there, your A minus, which is 1.0, goes there. That gives you your H plus ion concentration, and all I did from there to there was minus the log of that. So I mean, that's, you're probably not going to get one, I'm afraid, quite as easy as that in an exam situation. Okay, let's have a look at this. So I'll put this one on the board, and if you pause the video, do it, and then I'll scroll down, you can have a look at the answer. So you maybe want to pause the video there, do that. Okay, so this was another very simple one. You 0.4 moles of ethanoic acid, 0.5 moles of the salt of it, but it was all in 1 decimeter cube, 1,000 cubic centimeters, and you were given the Ka there. So the number of moles is equal to the concentration, well, simply because concentration equals number of moles divided by volume. Volume in this case is 1, okay, 1,000 over 1, which is, or 1,000 over 1,000, sorry, which is 1. And you should have got the values as so, and a pH of 4.86. Very simple one, again, similar to the one above. So let's look at this one here, slightly different again. I'll put it on the board. The answer's up there as well. I mean, you can have pause the video again, have a go at this one, or I'll talk you through it as well. So this one's slightly trickier. I wouldn't say it's a difficult one, but it's certainly slightly trickier, more representative perhaps of one that will come up in an exam. Right, this time we have 50 cc's of 0.3 molar acid and 150 of 0.3 molar salt, sodium ethanoate. The other thing, we've also been given the pKa, not the Ka, so we just need to convert our our pK into Ka. Just make sure and do that. Remember, if you do that, you will certainly get the wrong answer. Right, so what's the trick here? Well, the trick is, if I start off with 0.3 molar acid, okay, and I have 50 cc's of it, and I add 150 cc's of another solution to it, I'm going to change the concentration of that. So essentially I'm going from 50 cc's up to 200, so I'm diluting it by a factor of 4, which means if it was 0.3 to begin with, the new concentration of it is 0.3 divided by 4. It's 4 times as dilute because I've increased the volume from 50 up to 200. So that's what you had to cotton on to. If you just took this 0.3 value here and this 0.3 value here and put them into the equation like we did above, you'll get the wrong answer because the concentrations obviously change as you change the volume. So the new concentration of the weak acid is 0.075. Okay, that's your weak acid comp, your new one. Okay, right. The similar thing happens to the A minus, in that you had 150 cc's of it to begin with, and you dilute it up to 200. So you're not diluting by 4-fold this time, you're diluting by 200 over 150, which is 1.1 okay. So you take your original concentration, which we know up here is 0.3 for the salt, and we take our 0.3 and we find the new concentration by dividing it by the dilution factor, which is 1/3. So my new concentration of my salt is 0.225. Then all you have to remember is you just take your equation from earlier. Your HA is on the top line. Sometimes people get a bit confused with that. Your A minus is on the bottom line, and that gives you your H plus, and you just minus the log of that to give you 4.23. So we'll scroll down here to one that's similar to that. You can have a go at it. Okay. So the difference in this one is that we now have our 12 grams of ethanoic acid and our 4.1 grams of the sodium ethanoate. We've been given the Ka, so we don't need to convert pKa to Ka. But this time we have not a new equation, but an equation we haven't used before, where we've got moles equals mass over mR to bring into play on this occasion, and then we're going to link into concentration equals moles divided by volume. So I've said here it's slightly different, as we have masses and we need to convert those masses into moles and then into into concentrations. So very simple all the same. The moles of the acid is 12 divided by the RFM, which is 60.2 moles of the acid, and 4.1 divided by 82 gives us 0.05 moles of the salt. Remember, we've got to convert it into concentration. I don't actually, but we will anyway, just to keep things right. Okay. So we go up to here, concentration equals moles divided by volume. Our moles we've got here and here, so we divide both of those by volume, which is, remember, divide your volume, or put your volume into decimeters cubed, so it's divided by 0.1. Okay, and from there on in, we've got our new concentration of our acid, we have our new concentration of our salt ion. We remember to put the acid on the top line, our salt on the bottom line. That gives us our H plus. We minus the log of our H plus ions, concentration of our H plus ions, should say, and that gives us our new pH. Okay, so this one you want to have maybe if you pause the video there, you can see the question. Okay, so if you pause it, have a go at that. This is the same or very similar to the question, not the last question, but the question before that we did. So same sort of method. Okay, so pause the video, have a go at it, and then I'll scroll up. So I'm going to scroll up now. Okay, so there you go. Hopefully you can follow that calculation. We did our dilution factor again. This time we were going from 20 dilution, or a volume, sorry, of 20 up to 100, because we 20 plus 80. So we diluted by a factor of 5. So our original concentration was 0.1. It's now 0.1 over 5 for the acid, so it's 0.02. The salt went from 80 up to 100, so that was a dilution factor of 1.25. The original concentration of salt was 0.05, divided by 1.25 gives me 0.04, and then we just put our values in to the equation. We've got our Ka given to us, and we had 4.05 was our new pH there. Okay. Right, so we have another one here, very simple one, 22. If you look at 22, that's very simple. That's exactly the same as the one that we did right at the very start. So the examiner has given you all the values here. It can be just stick those values into the correct part of the formula with the Ka, get the H plus, minus the log of that. Right, so that's fine. We're looking really here in this question at part B and part C, which are a little bit more challenging than what we've done so far. So let's look at part B and part C. So what we're doing here in part B is now we're adding, and if you remember what I said about a buffer right at the start, we said that it was something that resists change in pH with addition of small amounts of acid or alkali. So we're going to add a little bit of acid in part B and then a little bit of alkali in part C. Okay, now if I added both of these amounts of acids or alkalis to just water on their own, the pH for part B would be between 0 and 1, I suspect, and for part C it would be between 13 and 14. Okay, so you're about to see how a buffer will change pH a very small amount with the addition of what is a considerable amount of acid and a considerable amount of alkali, but it has a very small impact on the pH of that buffer. So let's look how do we work this out when we add a certain amount of acid. So we're going to add 2 cubic centimeters of 5 moles per decimeter cubed hydrochloric acid to 1000 cc's of the buffer. So it makes it easier here that we've got 1000 cc's of the buffer. So that means that I know how many moles of acid I have because it's per decimeter cubed per 1000 cc's, and of course how many moles of salt I have, because again that's per 1000 centimeters cubed, 1 decimeter cubed. Okay, so it's a bit trickier. I've said here in B that it is a bit trickier, but it's not too bad. First thing that you need to do is you calculate the number of moles of the acid and the number of moles of the salt that you have in your buffer. Well, it's really easy this time, as I said, because you've got 1000 cc's of the buffer, so that tells you that you've 0.5 moles of the acid, 0.3 moles of salt. So that's really easy. Not always so easy, so bear that in mind, because you may get another one later where the volume is not 1000 cc's. In fact, you definitely will. Right. Now let's remind ourselves from lesson 1 then, how does a buffer actually work? Okay, well, a buffer works when you add acid to it. Okay, so if we look here, we add acid to it. It reacts with the A- ions, the salt ion, to give you acid. So therefore, in this instance, I'm adding acid to the buffer. So the A- ions, the salt ions, will decrease by the moles of the number of moles of hydrogen ions that you actually add. Okay, so in other words, this salt here will go down. Okay, so this value here for the A- that we have in our equation will decrease by the number of hydrogen ions that we add to the buffer. On the converse of that, the amount of acid that's in there will increase, because you can see here, when you add hydrogen ions to a buffer, you're making the acid. So when you add the acid, the number of moles of acid that you had in here, which was originally 0.5, will increase by the number of moles of hydrogen ions that you added. And if you increase the number of moles of acid here, and you decrease the number of moles of salt here, well, you're going to also alter the concentrations. So what we need to do in this calculation is work out how many moles of salt do I have now after I've added my acid. Okay, so how much does this drop by? And how many moles of acid do I have, and what are the new concentrations of those? Okay, so let's see how we do that. Okay, so we have added how much acid? We have added 0.02 decimeters cubed of 5 molar acid, which means I've added 0.01 moles of H plus ions. Okay, remember we said just above there that if I add, I'll just scroll down a little bit so we can see that. Okay, so we said if we add H plus ions, that means that the amount of acid goes up by that extent. Well, we added 0.01 mole of H plus ions. We had originally 0.5 moles of H plus ions, so we now have 0.51 moles of acid, or HA. That's my new moles of HA, recalculator. Remember, we said up here the number of moles of A- goes down as per the number of moles of acid added. So my new moles of A-, originally it was 0.3 moles. I have added 0.01 moles of acid, so they're going to go down by that extent. So my new moles of A- is going to be 0.029. Okay? Sorry, that's wrong. 0.29, I should say. Okay? Right, so the new concentration then, I've got to work out, because remember we've got to get the concentration. I have now got 0.51 moles of the acid, but it is now dissolved in 1000 cc's plus 2 cc's, so 1.002 gives me a new concentration of my acid of 0.51. Pop that in there. My concentration of my A-, 0.29 divided by 1000 plus the 2 cc's again from earlier. Okay, gives me 0.29 molar, or moles per decimeter cubed of the A-. Pop that in there. I have the Ka from the previous question. That gives me my H plus ions. Minus the log of that gives me a pH of 4.58. So originally the pH was 4.6. I've added some acid to it, quite a lot of acid in fact. I've only had a change of 0.02, so 2/100ths of a pH unit. Okay, so that's how you work out the pH change in a buffer when you add some acid to it. Let's have a look at how we do the same then if we add some alkali to it. So we have exactly the same calculation here, but this time we're adding alkali to it, and it's kind of the equal but opposite effect. So again, remember, we're adding hydroxide ions to it in part C of the question. Okay, 2 cubic centimeters, 5 molar hydroxide ions. That means we're adding 0.01 moles of hydroxide ions to my buffer. Remember what a buffer does when I add hydroxide ions to it. The hydroxide ions will react with the acid, and what will they do? Well, they will make salt. So this time it is the acid that decreases by the number of moles of hydroxide ions that are added, and it is the salt which increases by the number of moles of hydroxide ions that are added. So if we know the moles of acid that we had to begin with, 0.5, which it is up in the question, minus the number of moles of hydroxide, which is 0.01, gives me 0.49. Our new volume is 1.002, my 1,000 cubic centimeters, plus my 2 cubic centimeters, gives me a new concentration of HA of 0.49. That's the value I'll put into my equation. My new moles of salt will be the 0.3 moles that I started off with in the buffer, plus the number of moles of hydroxide gives me 0.31. Divide that by the new volume to give me concentration, comes out at 0.31. Plug those values into the formula that I had to get my H plus ions, minus the log of my H plus ions. 4.61 tells me when I add some hydroxide ions to it, we get an increase of pH of 0.02, so a very minimal increase in the pH considering the significant amounts of hydroxide ions that we added. Okay, so I'm going to scroll down to this one here. Okay, you maybe want to pause this. I'll give you and have a go at it. I'll give you a quick clue or a quick sort of help here. This time you're in volume, you're in mass of both, so you're going to have to use number of moles equals mass in grams divided by the RFM. And the other little thing you need to be careful of is that in your buffer for part B and part C, instead of having 1,000 cubic centimeters, you're down to 500 cubic centimeters. Okay, so we'll scroll down here, and if you want to pause it now, it'd be a good idea, and then I'll show the answers. Okay, so there's your answer to coming up now of part B. So 0.75 is the new pH there. If you want to pause that and maybe work your way through my workings out to check that you're along the right track, and then I'll scroll down to part C. So I'm going to scroll down to part C now. Okay, so for part C you can see there the pH again changed very, very slightly, only by 1/100th of a pH unit. So the answer is down here at 4.77. Okay, so hopefully that allows you guys to see how buffers, you can calculate the pH of a buffer first and foremost, then you can calculate the pH when you add some acid or some alkali to a buffer. I can't envisage A-level chemistry questions getting any more challenging than the ones that I've done there in this video. We're going to look in the next video at how we work out the pH of a buffer again, but this will be when we add an acid, an excess weak acid to a strong alkali. You've seen that was another method of making a buffer in video 1. Okay, I'm going to pop another little video in video 3 before I get to the second buffer one, because it will probably actually help you calculate the pH of a buffer from an excess weak acid and a strong alkali. This video number 3. Okay guys, I hope that helped, and you have plenty of questions in your notes, and Past paper questions also would be pretty useful here.